What if I told you that everything we can see, the stars, the galaxies, even the vast stretches of cosmic dust, makes up less than 5% of the universe? The rest, an invisible, enigmatic realm of forces so powerful they dictate the fate of the cosmos, yet so elusive we've barely begun to understand them. Picture this: galaxies racing away from each other at speeds that defy gravity's pull, as if some unseen hand is stretching the fabric of space itself. That's dark energy, one of the universe's most baffling puppeteers, silently shaping reality while remaining utterly hidden from our eyes. But dark energy is just the beginning. Beyond it lies a web of invisible forces, cosmic currents, phantom particles, and dimensions folded beyond our perception, each playing a role in the grand symphony of existence. Some tug at the strings of time, bending it like a river around a rock. Others whisper to matter, guiding it into the patterns we recognize as planets, stars, and life itself. These aren't just abstract ideas, they're the silent architects of everything we know, and they're hiding in plain sight. Imagine standing in a room where 96% of the furniture is invisible, yet you can feel its weight, its presence, its influence in every corner. That's our universe, a place where the unseen outnumbers the seen in ways that still leave scientists speechless. Today, we're pulling back the curtain on these mysteries. From the ghostly pull of dark matter to the quantum ripples that birth the cosmos, we'll explore 30 forces that shape reality itself. Some are familiar, lurking in the equations of physics. Others are so strange they sound like science fiction until you realize they're the reason you exist at all. This isn't just a journey through space and time. It's a detective story, a hunt for the hidden threads weaving the tapestry of existence. And by the end, you'll never look at the night sky the same way again. So let's begin, because the universe's greatest secrets are waiting just beyond the edge of the light. In the vast darkness between galaxies, something strange is happening. Space itself is stretching faster than it should. This isn't just empty expansion. It's an unstoppable push, a force so powerful it overrides even gravity's pull. Scientists call it dark energy, and its discovery in 1998 turned cosmology upside down. The clue: distant supernova, exploding stars so far away their light took billions of years to reach us. But instead of appearing dimmer as expected, they were too faint, proof the universe wasn't just expanding but accelerating. Think of it like throwing a ball into the air, only to watch it shoot away faster the higher it goes. That's dark energy's work, a kind of anti-gravity woven into the fabric of space. While dark matter huddles galaxies together with its invisible grip, dark energy does the opposite, pushing everything apart, stretching the cosmos into an ever thinner void. Picture an inflating balloon, but one where the rubber grows stronger as it expands, making the process unstoppable. What's truly unsettling: we have no idea what dark energy actually is. Some theories suggest it's the energy of empty space itself, a property Einstein once called the cosmological constant before dismissing it as his greatest blunder. Others propose undiscovered particles or even flaws in our understanding of gravity. But here's the spine-tingling question: if dark energy keeps strengthening, could it one day rip apart galaxies, stars, even atoms? The fate of the universe might hinge on an invisible force we're only beginning to detect. A reminder that the cosmos holds mysteries far stranger than fiction. While dark energy pushes the universe apart, another invisible force holds it together: dark matter, the cosmic glue that binds galaxies against the relentless stretch of space. Picture a spinning carousel. If it were just the horses you could see, physics says the outer ones should fly off as it spins faster. Yet when astronomers measured galaxy rotation, they found stars at the edges whirling just as fast as those near the center, defying gravity's rules. The explanation: an enormous halo of unseen matter, its gravitational pull keeping stars from escaping like hidden anchors in the cosmic dark. This isn't just theory, we've watched dark matter bend light itself. When distant galaxies appear strangely warped or duplicated across the sky, it's because dark matter's gravity acts like a cosmic magnifying glass, twisting the fabric of space so severely that light detours around it. One of the most striking examples, the Bullet Cluster, where two galaxies collided and their dark matter left ghostly fingerprints visible only because it tugged the light of more distant stars, leaving ordinary matter far behind. Yet for all its influence, dark matter remains maddeningly elusive. Unlike atoms, it doesn't absorb, reflect, or emit light, hence the dark in its name. Scientists suspect it could be exotic particles, trillions of which might be streaming through you right now. Experiments like LUX Zeppelin hunt for these phantoms in miles-deep underground labs, shielded from cosmic noise, waiting for the faintest bump of a dark matter particle hitting ordinary material. But here's the mind-bending twist. What if dark matter isn't just particles, but an entire shadow universe? Some theories suggest it could have its own forces, even its own structures, parallel galaxies made of stuff we can't see or touch, woven into the same space we occupy. Imagine two worlds overlapping, one luminous, one invisible, both shaping the cosmos in ways we're only beginning to decipher. Every galaxy we see might be just the tip of an iceberg, with 90% of its mass lurking in the dark, a reminder that reality is far stranger than the limits of our eyes. Now imagine a place where nothingness isn't really empty, where even the void itself crackles with invisible energy. This is the quantum vacuum, a seething ocean of particles and antiparticles flickering in and out of existence so fast they defy everything we think we know about reality. These aren't just theoretical ghosts, they've been caught in action, bending the rules of physics in ways that still baffle scientists. Take the Casimir effect. Two metal plates placed incredibly close together in a vacuum. According to classical physics, nothing should happen, but in reality, the plates get pushed together. Why? Because the quantum foam of virtual particles outside the plates exerts more pressure than the limited particles that can exist between them. It's like standing in a crowd where the people outside are shoving harder than the ones inside, forcing you closer to the person next to you, except here, the people are particles that vanish before we can even see them. Then there's Hawking radiation, the eerie glow that black holes emit despite supposedly trapping everything, even light. Stephen Hawking realized these quantum fluctuations near a black hole's edge could allow one particle to escape while its partner falls in, slowly draining the black hole's energy. That means even the darkest gravitational monsters might eventually evaporate, thanks to particles materializing from what we thought was empty space. But here's the wildest part. This quantum foam isn't just a curiosity, it might hold the key to the universe's ultimate energy source. Zero-point energy, the baseline hum of the vacuum, suggests that even at absolute zero, space is far from still. Some theorists believe harvesting this energy could revolutionize civilization, powering starships or entire cities with the universe's own restless flickering. Of course, we're nowhere near that technology yet, but the fact that it's even a possibility shows just how little we truly understand about the nothingness all around us. And that's the real shock. The quantum vacuum isn't passive. It's an active, writhing medium that might have played a role in the Big Bang itself, seeding the universe with the fluctuations that became galaxies. So next time you look at the night sky, remember, you're not just staring at the vast emptiness of space, you're peering into a hidden storm of creation and destruction where particles dance in and out of existence, shaping reality itself. What if the entire universe was once smaller than a grain of sand, then exploded to cosmic size in less than the blink of an eye? That's cosmic inflation, a turbocharged expansion in the first sliver of a second after the Big Bang, stretching space so fast it left ripples in the very fabric of reality. Imagine blowing up a balloon with microscopic wrinkles. The more it inflates, the smoother its surface appears. That's precisely what inflation did to our universe, smoothing out the primordial chaos into the eerie uniformity we see today in the cosmic microwave background, the afterglow of creation itself. Those faint temperature variations in the CMB, they're the fingerprints of quantum fluctuations stretched to cosmic scales, seeds that grew into galaxies and superclusters. Without inflation, the universe would resemble a lumpy, uneven mess. Instead, we see a horizon where distant regions, billions of light-years apart, share nearly identical temperatures, something impossible unless space expanded faster than light itself. Here's the kicker: inflation wasn't just a one-time event. Some theories suggest it never fully stopped, continuing in distant pockets of space, spawning new universes like bubbles in an endless cosmic froth. Could our entire observable universe be just one bubble in an infinite multiverse, each with its own laws of physics? It's a dizzying thought. Inflationary models hint that these bubble universes might collide, leaving scars in the CMB, hints of other realities brushing against our own. And if inflation is eternal, as some physicists propose, then new universes are constantly being born, each a separate experiment in the laws of nature. The craziest part, we might never know for sure. Inflation happened so early, so violently, that its energy scales dwarf anything our particle colliders can recreate. Yet its echoes are everywhere in the large-scale structure of galaxies, the uniformity of the CMB, even the flat geometry of space-time. It's as if the universe left us breadcrumbs, clues to its most explosive secret. So when you look up at the night sky, remember, the vast, smooth expanse above you might just be the aftermath of the greatest stretch in history, one that set the stage for everything from the first stars to the atoms in your hands. Deep in the chaos of the early universe, black holes may have formed not from collapsing stars, but from the raw fury of the Big Bang itself. These primordial black holes are cosmic relics, some as small as a grapefruit, yet packing the mass of a mountain. Unlike their star-born cousins, they didn't need a supernova to exist. They could have blinked into being from the densest wrinkles of space-time in the universe's first violent seconds. And here's the spine-tingling possibility. These ancient leftovers might be lurking everywhere, invisible and undetectable, until they betray their presence by warping the very fabric of reality around them. Imagine a black hole no wider than your front door, yet dense enough to bend starlight like a lens. When one passes between us and a distant star, its gravity briefly magnifies the star's light, an event called microlensing. Astronomers have seen these mysterious flashes for decades, and some could be the calling cards of primordial black holes drifting unseen through the galaxy. Even more intriguing, they might solve one of cosmology's biggest puzzles. If enough of them exist, these tiny gravitational traps could account for the missing mass we call dark matter, hiding in plain sight while sculpting the universe's structure. But there's a twist. According to Hawking radiation, small black holes shouldn't last forever. Quantum effects near their event horizons make them slowly evaporate, emitting particles until they vanish in a final, explosive burst of energy. A grapefruit-sized primordial black hole would take about the age of the universe to disintegrate, meaning if they were common after the Big Bang, we should be detecting their death screams as gamma-ray flashes. Yet the sky remains eerily quiet, leaving scientists to wonder, did most evaporate long ago, or are they out there, silent and patient? The most unsettling question of all, could one be closer than we think? The Oumuamua cloud, that icy debris field at the solar system's edge, is the perfect hiding place for a primordial black hole. Its gravity could explain the odd orbits of some distant objects like the hypothetical planet 9, except instead of a frozen world, it might be a pinprick of infinite density, subtly tugging at everything around it. Future telescopes could hunt for the telltale heat signature of a tiny black hole absorbing cometary material, or the ripples it creates in the solar system's delicate dance. Whether as dark matter candidates or cosmic time capsules, primordial black holes force us to rethink the universe's infancy. They're remnants of a time when the laws of physics were stretched to their limits, surviving billions of years to whisper secrets about the conditions of creation itself. And if they're real, they prove that even the smallest objects can hold the universe's greatest mysteries. Magnets are all around us, from the ones stuck to your fridge to the ones guiding compass needles, and every single one has two poles, a north and a south. Break a magnet in half and you don't isolate a pole, you just get two smaller magnets, each with its own pair of opposing ends. But what if nature hid a secret in the early universe, a particle with just one magnetic pole? That's the tantalizing mystery of magnetic monopoles, a hypothetical cosmic rebel that could shatter our understanding of physics. Grand unified theories, ambitious frameworks aiming to merge the fundamental forces, predict these solitary poles should exist. In the extreme heat of the universe's first moments, space might have bubbled with them like defects in cooling metal. Yet despite decades of searching, from deep underground labs to cosmic ray detectors, not a single confirmed monopole has been found. Their absence isn't just a curiosity, it's one of the strongest clues that cosmic inflation really happened. If the universe ballooned exponentially in size moments after the Big Bang, it would have stretched these relics so thin they'd be virtually undetectable today, like drops of ink in an ocean. But what if we've been looking in the wrong places? Some theorists speculate monopoles could be hiding in the hearts of neutron stars, those ultra-dense corpses of dead suns. The crushing gravity and bizarre quantum conditions inside might trap or even create these elusive particles, preserving them like fossils in a cosmic museum. Others suggest monopoles could be masquerading as dark matter, their weak interactions making them nearly invisible until they reveal themselves by tearing through atoms in a way no ordinary particle could. Finding even one monopole would be revolutionary. Unlike electrons or quarks, their existence would prove that magnetism isn't just a side effect of moving charges, it's a fundamental force with its own unique building blocks. It could explain why electric charge comes in fixed quantized amounts and why the universe seems fine-tuned for life. So why does their absence matter? Because sometimes what we don't find tells us more than what we do. The missing monopoles hint at an epoch of unimaginable expansion, a moment when the laws of physics themselves were reborn. They're ghostly signposts pointing back to the universe's first trillionth of a second. And if we ever catch one, it won't just rewrite textbooks, it'll rewrite reality. Every second, trillions of invisible particles pass straight through your body, and you'd never know it. These are neutrinos, the universe's ultimate ghosts, so reluctant to interact with matter that most will travel through light years of lead without a single collision. But in the late 20th century, scientists discovered something astonishing. Neutrinos aren't just passive spectators, they're shape-shifters. On their journey through space, they oscillate between three distinct flavors: electron, muon, and tau, like a chameleon cycling through colors mid-stride. And this bizarre behavior holds a revolutionary secret. Neutrinos must have mass. The discovery shattered decades of assumptions. According to the standard model, neutrinos should be massless like photons. But when detectors caught fewer neutrinos arriving from the sun than predicted, and realized the missing particles hadn't just vanished but transformed, it forced physics to rewrite the rules. Even more compelling, the dramatic neutrino burst from supernova 1987A. When that star exploded in the Large Magellanic Cloud, detectors on Earth picked up 24 neutrinos hours before the light reached us. The fact that they arrived in distinct flavor groups after traveling 160,000 light-years proved oscillation wasn't just a lab curiosity, it was a cosmic phenomenon. Now, projects like DUNE, the Deep Underground Neutrino Experiment, aim to unravel these particles' mysteries using beams shot through 800 miles of Earth's crust. By studying how often neutrinos switch flavors over long distances, scientists hope to crack one of the universe's biggest puzzles: why matter dominates over antimatter. If neutrinos and their antiparticles oscillate differently, they could explain why the early universe didn't annihilate itself into pure energy, leaving behind the atoms, planets, and people we see today. Here's why this matters. Neutrinos might be the only particles that feel both gravity and the weak nuclear force, making them potential messengers between the quantum realm and cosmic scales. Their vanishingly small mass could hint at extra dimensions or undiscovered physics beyond the standard model. And because they're born in the hearts of stars, supernova, and even Earth's own radioactive decay, they offer a backstage pass to the universe's most violent events. So next time you feel nothing, remember, you're swimming in an ocean of phantoms, billions of neutrinos from the sun, distant galaxies, and the Big Bang itself are piercing through you every second, rewriting the story of reality one oscillation at a time. And with each new detector buried under mountains or ice, we're inching closer to deciphering their silent language, a code that might just explain why anything exists at all. Imagine a universe where every particle, electrons, quarks, even you weighed nothing at all. No gravity, no atoms, no stars. That could have been our reality if not for an invisible cosmic syrup called the Higgs field, stretching through all of space like an endless ocean. When particles move through it, they don't glide effortlessly. They slog forward as if wading through molasses, and that resistance is what we experience as mass. The faster a particle interacts with this field, the heavier it becomes. Photons, those weightless messengers of light, zip through untouched, but electrons. Quarks, they're constantly bumping into Higgs bosons, the field's ripples like swimmers fighting a current. This bizarre cosmic treacle wasn't just theorized, it was caught. In 2012, scientists at CERN Large Hadron Collider announced they'd spotted the Higgs boson after smashing protons together at nearly light speed. The collision's energy briefly shook the Higgs field hard enough to create a ripple, a particle that decayed almost instantly into other, more familiar ones. It was like seeing the splash of a fish nobody could see, only deducing its existence from the ripples left behind. That discovery completed the standard model, but it also opened a terrifying question. What if the Higgs field isn't as stable as we think? Here's where things get eerie. The Higgs field didn't always give particles mass. In the universe's first moments, it sat in a high-energy state, like a marble balanced on a hilltop. As the cosmos cooled, that marble rolled downhill, settling into the valley we know today, a process called symmetry breaking. But some theories suggest there might be deeper valleys, lower energy states the Higgs field hasn't found yet. If something jostled it, a quantum fluctuation, a collision with cosmic strings, the field could suddenly tumble into this new state, rewriting physics in an instant. Picture a bubble of this new reality expanding at light speed, erasing the old laws as it goes. Atoms would unravel, stars would blink out, the very forces holding nuclei together would vanish. And because this bubble's edge would move faster than light, we'd never see it coming. It sounds like science fiction, but the math doesn't lie. The Higgs field's current state might be metastable, stable for now, but not forever. Then again, the universe is 13.8 billion years old, and it hasn't happened yet. Maybe we're safe, or maybe we're just lucky. Yet the Higgs field's fragility is also its gift. Without that delicate balance, particles would never have gained mass, gravity would never have sculpted galaxies, and life as we know it couldn't exist. It's the ultimate cosmic tightrope act, and we're all walking it right now. So next time you feel the weight of your body in a chair, thank the Higgs. That heaviness isn't just physics, it's the universe holding you together. Picture the universe in its earliest moments, a seething, chaotic place where space and time hadn't yet settled into the smooth fabric we know today. If you could peer into that frenzy, you might spot cracks forming in reality itself, like flaws in cooling glass. These defects, called cosmic strings, could still be lurking out there, threads of pure space-time curvature, thinner than a proton but stretching across the cosmos, each with the mass of a mountain range packed into every inch. And they're not just relics, they might be bending light, warping time, and humming with the echoes of the Big Bang. Some theories suggest these strings could act as natural time machines. Imagine a string moving at near light speed, twisting spacetime around it into a loop. If two strings crossed or a single string kinked, they might create closed time-like curves, paths that circle back on themselves, allowing hypothetical travel into the past. Of course, the energy required to manipulate a cosmic string is beyond anything we could muster, but the fact that the universe might have woven time travel into its own structure is mind-bending enough. Even stranger, cosmic strings could be ringing like guitar strings, vibrating with the energy of the early universe. These trembles wouldn't produce sound but something equally dramatic: gravitational waves. Unlike the fleeting ripples from black hole collisions, a cosmic string's waves would be relentless, spanning frequencies so low they'd take years to oscillate. Pulsar timing arrays networks of dead stars whose rotations are as precise as atomic clocks are listening for these waves. A single string's passing could tweak the rhythm of pulsars light years apart, like a spider's thread disturbing a web. Then there's the lensing effect. A cosmic string's immense density would slice through spacetime like a wire through cheese, creating duplicate images of galaxies behind it. Astronomers have searched for these telltale twin quasars, but so far, no definitive string has shown itself. Yet the most tantalizing possibility remains. What if we're not looking for something still here, but its ghost? When strings snap or decay, they might release bursts of energy visible as fast radio bursts, or even imprint a faint pattern in the cosmic microwave background, a snapshot of the universe's violent infancy. Could one of these strings be drifting through our galaxy right now? If so, it's silent, invisible, and unimaginably ancient, a fossil from the first trillionth of a second after creation. And if we ever find it, we won't just be uncovering a curiosity. We'll be holding a piece of the universe's original blueprint, a thread woven into reality before time itself had meaning. For decades, scientists assumed dark matter was made of heavy, sluggish particles, the so-called WIMP, or weakly interacting massive particles. But what if the truth is far stranger? Enter actions, hypothetical particles so lightweight they'd make a feather seem massive by comparison. These ghostly specks were first dreamed up to solve a cosmic puzzle called the strong CP problem, a mystery about why certain subatomic interactions don't mirror each other perfectly, despite all known physics suggesting they should. The math hinted at a missing piece, a subtle cosmic symmetry keeper, and in 1977, physicist Roberto Pexi and his student Helen Quinn proposed a radical fix, a new field pervading the universe whose ripples would manifest as particles' actions. Unlike their burly WIMP cousins, actions would be almost absurdly delicate, with masses billions of times smaller than an electron. But here's the catch: they'd also be absurdly abundant. If actions exist, they'd outnumber atoms in the universe by a factor of trillions, forming a fine, invisible mist that clumps into halos around galaxies. Their gravitational pull would explain why stars orbit galaxies faster than visible matter can account for without actions ever bumping into ordinary stuff. You could be swimming in an ocean of them right now, feeling nothing as they slip through you like sunlight through glass. Hunting these phantoms takes ingenuity. Projects like ADMX, the Action Dark Matter Experiment, turn microwaves into particle traps. Inside a powerful magnetic field, actions should occasionally convert into faint photons, producing a telltale signal. ADMX ultrasensitive detectors listen for this whisper, tuning their radio across frequencies like a cosmic dial, hoping to catch the exact pitch of an action song. The stakes couldn't be higher. If actions are real, they'd solve two mysteries at once: the nature of dark matter and the strong CP problem. They'd also hint at a universe far more intricate than we imagined, where even the tiniest particles hold galaxies together. And if they're not, well, the hunt itself is stretching the limits of technology, proving that sometimes the search for nothing can lead to everything. Deep in the direction of the constellations Centaurus and Hydra, something invisible is pulling thousands of galaxies, including our own, toward it at mind-bending speeds. Astronomers call it the Great Attractor, a gravitational anomaly so powerful it bends the motion of entire galaxy clusters, yet remains hidden behind the thick dust and stars of the Milky Way's disk. Imagine standing in a dense forest, hearing the roar of a distant waterfall but unable to see it through the trees. That's our predicament, an unseen force dragging us toward a point 250 million light-years away, and we're stuck peering through the cosmic equivalent of fog. Redshift maps reveal the scale of this mystery. By measuring how light from distant galaxies stretches as they move away from us, scientists have traced a river-like flow of galaxies all streaming toward the same invisible destination. The Virgo supercluster, our galactic neighborhood, is caught in this current, racing toward the Great Attractor at over 600 kilometers per second. But here's the twist: the mass we can see in that region, galaxies like the Norma cluster, doesn't come close to explaining the pull. There's a colossal amount of missing matter warping space-time, and it's not just dark matter. This might be the heart of the Laniakea supercluster, a web of galaxies spanning 500 million light-years, with the Great Attractor as its gravitational anchor. Yet some theories suggest it could be something even stranger. Could a supermassive black hole billions of times heavier than the Sun lurk there? Or a concentration of dark energy warping the fabric of space itself? The answer might lie with the square-kilometer array, the SK telescope, set to scan the hidden zone with unprecedented detail. Using radio waves that pierce the Milky Way's dust, it could map the Great Attractor's true structure, revealing whether it's a known cosmic heavyweight or a phenomenon we've never imagined. One thing's certain: as the Milky Way hurtles toward this enigma, we're not just observers. We're caught in its grip, passengers on a collision course with a mystery written in gravity's invisible ink. And when the veil finally lifts, we might discover that the universe's largest structures are even grander and stranger than we dared to guess. Einstein showed us that gravity isn't just the pull of mass, it's the warp and weave of spacetime itself. And if that's true, then anything with enough energy, even something as weightless as light, could theoretically bend spacetime into a black hole. Picture this: a single point where photons, those massless particles of pure energy, are so densely packed that their collective gravity traps them forever. This is the mind-bending concept of a Kugelblitz, German for ball lightning, a black hole born not from collapsing matter, but from the sheer intensity of light itself. The math checks out. Einstein's equations reveal that if you could focus enough electromagnetic energy into a tiny volume, space-time would buckle under its own weight, forming an event horizon just like a stellar black hole. But here's the catch: the energy required is almost unimaginable. We're talking about compressing the output of a star or an entire galaxy's worth of lasers into a space smaller than an atom. Yet in theory, it's possible. Some lab experiments have taken baby steps toward this extreme. Ultra-high-intensity lasers, like those at the European Extreme Light Infrastructure, can briefly create conditions where light's energy density approaches the thresholds needed to warp spacetime measurably. While we're nowhere near forging a Kugelblitz, these experiments hint at a future where we might manipulate gravity itself using pure energy. Now for the sci-fi twist. Imagine a civilization advanced enough to engineer Kugelblitz black holes as power sources. Unlike traditional black holes, which evaporate over eons via Hawking radiation, a Kugelblitz fed by lasers could be stabilized, a self-sustaining gravity battery. Need to power a starship? Contain a tiny Kugelblitz in a magnetic trap, harvest its radiation, and you've got an engine that could outlast the stars. But the risks are apocalyptic. One miscalculation and your artificial black hole could sink through the floor, devouring the planet from within. The wildest implication. If light can create black holes, then spacetime might be far more fragile than we thought. In the chaotic early universe, quantum fluctuations alone could have birthed fleeting Kugelblitzes, black holes popping in and out of existence like bubbles in a boiling pot. Some theorists even suggest these primordial photon holes might still lurk in the cosmos, disguised as dark matter. So while we're centuries away from bottling starlight into a singularity, the mere possibility reshapes how we see reality. Gravity isn't just about mass, it's about energy, motion, and the hidden threads stitching the universe together. And if a Kugelblitz is possible, then the universe's most destructive force might just be a beam of light waiting to be focused. The universe might be sitting on a bubble one that could pop at any moment. This nightmare scenario is called vacuum decay, and it starts with a deceptively simple idea. What if the emptiness of space isn't truly empty but trapped in a fragile state, like a marble balanced on the edge of a bowl? Right now, the quantum fields that fill our universe, including the Higgs field, appear stable. But if they're not in their absolute lowest energy state, a single quantum fluctuation could tip them into the true vacuum, unleashing a catastrophe that rewrites physics at the speed of light. Think of it like an ice cube in a glass of water. At freezing temperatures, the ice seems stable until a tiny nudge makes it suddenly melt. Our universe could be in a similar false vacuum, seemingly solid but actually metastable. The math behind this is terrifyingly real. Calculations of the Higgs field stability suggest it might not be in the true vacuum state, meaning a single random event, say a high-energy particle collision, could nucleate a bubble of true vacuum. This bubble would expand at light speed, its walls rewriting the laws of physics as they pass. Inside, atoms disintegrate, forces unravel, and reality as we know it ceases to exist. The worst part, you'd never see it coming because the bubble's edge moves faster than any warning signal. Some theories suggest this might have already happened elsewhere. If a true vacuum bubble formed in some distant galaxy billions of years ago, its destruction could be racing toward us right now, invisible until the instant it arrives. But here's the twist. The fact that we're still here suggests either the universe is more stable than we think, or we're living on borrowed time. Experiments at the Large Hadron Collider constantly probe the Higgs field's properties, searching for clues about its ultimate fate. The numbers hover on a knife's edge, a Higgs mass just a few percent lighter, and the universe would have collapsed long ago. A fraction heavier and vacuum decay would be impossible. So are we perched on a cosmic tightrope, one quantum fluctuation away from oblivion? Or is the universe more resilient than our equations suggest? The answer might lie in the spaces between atoms, where the fabric of reality hums with hidden energy, waiting for now to stay exactly as it is. Until it doesn't. The cosmic microwave background should be a random snapshot of the early universe, a perfectly uniform glow with tiny, unpredictable temperature fluctuations like static on an old television. But in 2005, astronomers uncovered something unsettling. When they mapped these faint ripples across the sky, they noticed an eerie alignment. The largest temperature variations weren't scattered randomly. Instead, they traced a pattern eerily aligned with the plane of our solar system. Scientists grimly dubbed it the axis of evil because, if true, it threatens one of cosmology's most sacred assumptions, the Copernican principle, the idea that Earth holds no special place in the universe. At first, researchers dismissed it as a fluke. After all, the CMB is incredibly faint, buried under interference from galactic dust and the Doppler effect of our own motion. But the more data we collected, from WMAP to Planck, the stranger it looked. The odds of such an alignment happening by chance are less than 1 in 1,000. Some theorists suggest it could be contamination from local structures, like the gravitational pull of the nearby Virgo supercluster subtly warping the CMB's signal. Others propose an even wilder explanation. What if this axis isn't an illusion but a fossil, a relic from before the Big Bang imprinted on space-time like a scar. Imagine the universe not as a one-time explosion, but as a cycle, a bouncing cosmos where each Big Bang is preceded by a collapse. In that scenario, remnants of a previous epoch might survive, leaving faint patterns in the CMB like echoes in a cave. Alternatively, the axis could hint at something more profound, a cosmic anisotropy, a fundamental lopsidedness woven into the fabric of reality itself. If spacetime has a preferred direction, it would rewrite everything we know about inflation and the universe's expansion. Yet the most unsettling possibility remains: what if we're wrong about being cosmically insignificant? The axis of evil might not mean Earth is special, but it does suggest our solar system is weirdly synchronized with the universe's largest-scale structures. Like a compass needle inexplicably pointing toward your hometown, it forces us to question whether we're seeing a statistical ghost or the first crack in the foundation of modern cosmology. Future observatories like the CMB-S4 project aim to settle the debate with unprecedented precision. Until then, the axis stands as a chilling reminder: the universe might not be as random as we thought. And that's either a clue to its deepest secrets or the ultimate cosmic prank. What if you could build a clock that ticks forever without ever needing to be wound? Meet time crystals, the bizarre quantum structures that break one of nature's most fundamental rules, the arrow of time itself. Unlike ordinary crystals, which arrange atoms in repeating patterns through space, time crystals repeat their patterns through time, oscillating between states indefinitely without any energy input. It sounds like perpetual motion, a fantasy outlawed by thermodynamics, yet in 2016, researchers at the University of Maryland built one using a chain of ytterbium atoms, nudged into rhythm with laser pulses. The result, a quantum metronome that never winds down, locked in an eternal dance between order and chaos. How is this possible? Time crystals exploit a loophole in symmetry. Normally, if you shake a system periodically, say, tapping a pendulum every second, it will sync up with your taps. But time crystals resist this synchronization, responding at a slower rhythm, like a drummer ignoring the conductor's beat. This time symmetry breaking was once thought impossible outside of theory. Yet labs have since created time crystals in diamond defects, superfluid helium, and even quantum computers, each one a tiny rebellion against time's relentless forward march. The implications are staggering. Imagine a clock that keeps perfect time until the heat death of the universe, or quantum computers stabilized by these self-sustaining loops. Some theorists suggest time crystals might even lurk in exotic materials like spin ice, their hidden rhythms driving mysterious properties, but the real mind-bender. If time crystals can exist without energy input, could the universe itself be one? Think about it. The cosmos is filled with repeating cycles, pulsars flashing, galaxies rotating. Could these be fractal echoes of a primordial time crystal, a structure woven into space-time at the Big Bang? It's a wild idea, but not impossible. After all, if tiny ytterbium atoms can defy time's arrow in a lab, who's to say the universe didn't start with its own eternal heartbeat? One thing's certain: time crystals prove reality has surprises left, and some of them might be ticking silently right under our noses. In 2016, NASA made headlines with an engine that seemed to defy the laws of physics, the M drive, a tapered copper chamber that allegedly produced thrust without expelling any fuel. According to Newton's third law, every action must have an equal and opposite reaction. Rocket engines push exhaust backward to move forward, but the M drive, it just moved as if it could bend momentum to its will. The numbers were tiny, a few micronewtons of force, barely enough to nudge a sheet of paper, but if real, it promised to revolutionize space travel. No fuel, no giant tanks, just acceleration from seemingly nowhere. Skeptics were swift. The thrust measurements were achingly close to the margin of error, and some tests suggested thermal expansion of the device itself could explain the wobble. Yet the controversy deepened when independent teams, including one at Germany's Dresden University, reported similar anomalous thrust in their own M-drive experiments. The most tantalizing theory, quantum vacuum fluctuations. The engine's microwaves might have been pushing against a sea of virtual particles popping in and out of existence, borrowing momentum from the universe itself. It was a wild idea, one that, if true, would mean empty space isn't empty at all, but a frothing ocean of untapped energy. Then came the crushing blow. In 2021, a painstaking study by TU Dresden found that thrust was likely just magnetic interference from Earth's field interacting with the device's power cables. No violation of physics, no free momentum, case closed. Not quite, because here's the twist. Even after the debunking, a handful of researchers kept digging. They wondered, what if the M-drive wasn't entirely wrong, just misinterpreted? What if the real anomaly wasn't thrust, but some subtler quantum effect we haven't yet pinned down? The M-drive's legacy isn't just about a failed experiment. It's a cautionary tale about how desperately we want to believe in breakthroughs, and how hard it is to kill an idea that feels like it's dangling a cosmic cheat code. Because somewhere between measurement errors and unanswered questions, there's still a whisper. What if we're missing something deeper, not magic, but physics we haven't yet written? After all, the universe has surprised us before, and sometimes the most impossible ideas are the ones that push science forward even when they're wrong. Black holes aren't just cosmic vacuum cleaners, they're the universe's ultimate shredders. When something crosses the event horizon, it's gone, right? Not just gone, but erased so thoroughly that not even light can escape. But here's the problem. Quantum mechanics says information, the fundamental details of every particle, every atom, can never truly vanish. It might get scrambled, transformed, or hidden, but it must persist. So when a black hole eventually evaporates via Hawking radiation, what happens to all that swallowed information? This is the black hole information paradox, a clash between gravity and quantum theory so deep it's kept physicists awake for decades. Stephen Hawking first spotted the contradiction in the 1970s. His calculations showed black holes emit radiation, slowly losing mass until they disappear. But that radiation appeared random, carrying no trace of the original matter that fell in. It's like burning a library and claiming the smoke particles somehow encode every book's contents, except no one could find the cipher. The implications were terrifying. If black holes really delete information, the entire foundation of quantum mechanics, with its precise predictability, collapses. Enter the firewall theory, a radical fix that's as brutal as it sounds. Maybe the event horizon isn't a smooth gateway, but a searing wall of energy, incinerating anything that touches it. Information wouldn't vanish, it'd be scorched into Hawking radiation at the boundary. But this creates its own nightmare. General relativity insists falling into a black hole should feel like nothing. No walls, no fire, just the gentle pull of gravity. So do we rewrite Einstein or quantum physics? Then there's the holographic principle, a mind-bending escape hatch. What if all the information swallowed by a black hole isn't lost inside but smeared across its surface like a cosmic DVD? The idea suggests reality might be a projection, with the event horizon acting as a pixelated screen encoding 3D events in 2D data. It sounds like sci-fi, but the math has held up. Experiments with quantum entanglement even hint that particles inside and outside a black hole could be linked, preserving information through invisible threads. The wildest take, black holes might not be the end but a transformation. Like water turning to steam, matter could dissolve into pure information, woven into the fabric of spacetime itself. If true, the universe operates like a colossal computer with black holes as its recycling bins. So the next time you look at the night sky, remember, even the darkest voids might just be hiding secrets in their shadows, waiting for us to crack the code. Rising from the heart of the Milky Way like two colossal glowing balloons, The Fermi bubbles stretch 25,000 light-years above and below our galaxy's disk, an eerie pair of structures blazing with gamma rays. Discovered in 2010 by NASA's Fermi telescope, these titanic lobes are invisible to the naked eye, yet they radiate with the energy of 100,000 supernovae. The question is, what could possibly leave such a scar on the cosmic sky? One leading suspect sits at the very center of the Milky Way, Sagittarius A, our galaxy's supermassive black hole. Astronomers suspect that roughly 2 million years ago, this sleeping giant might have woken in a violent feeding frenzy, swallowing a massive cloud of gas or even a star. The resulting explosion would have blasted jets of energy straight up and down from the galactic plane, inflating these bubbles like a cosmic blowtorch. Supporting this theory are traces of ancient shockwaves in the Magellanic Stream, a ribbon of gas orbiting the Milky Way, which appear to have been scorched by a long-ago eruption from the galactic core. But there's a twist. Not everyone believes Sagittarius A is the culprit. Some scientists argue the Fermi bubbles could be evidence of something even stranger: dark matter annihilations. If dark matter particles collide and destroy each other, they'd release bursts of gamma rays, potentially creating these vast structures. The bubble's symmetrical shape and energy signature fit certain dark matter models, adding fuel to this speculative fire. Yet critics point out that if dark matter were responsible, similar structures should appear around other galaxies. So far, none have been found. The most tantalizing clue might be hidden in the bubbles themselves. Their edges are unnervingly sharp, like they were carved by a sudden, violent event rather than a slow leak of energy. This suggests a rapid, cataclysmic outburst, something akin to a black hole burping after a colossal meal. If true, it means our galaxy's heart isn't as dormant as it seems. Sagittarius A might be capable of periodic eruptions, reshaping the Milky Way in ways we're only beginning to understand. What's certain is that the Fermi bubbles are a reminder of how dynamic and dangerous our galactic home really is. Whether from a black hole's tantrum or dark matter's hidden fireworks, they prove that even the quietest corners of the cosmos can hold echoes of unimaginable violence. And if Sagittarius A truly woke once, it could wake again, turning those faint gamma-ray ghosts into a beacon of something far more explosive. On August 15, 1977, a radio telescope in Ohio picked up a signal so powerful and so strange that the astronomer who discovered it scrawled, "Wow," in the margin of the printout, and gave birth to one of the greatest cosmic mysteries of all time. For 72 seconds, the Big Ear telescope recorded a narrowband radio burst at 1420 MHz, a frequency near the hydrogen line where scientists had long predicted an alien civilization might broadcast. The signal was 30 times louder than the background noise, matched no known celestial object, and vanished as suddenly as it appeared. It came from the direction of the constellation Sagittarius, a region with no stars in that exact spot, just empty space. And 47 years later, we still have no idea what caused it. The WOW signal checks every box for what extraterrestrial intelligence might sound like. It was a concentrated, single-frequency transmission, the kind you'd expect from a deliberate beacon rather than a natural cosmic accident. Hydrogen, the most common element in the universe, would be a logical calling card for any civilization trying to get noticed. And the signal's intensity suggested an origin far beyond anything humans could produce at the time, ruling out a secret military test or satellite glitch. Skeptics have tried to explain it as a passing comet, interstellar plasma, or even a reflected Earth-based transmission, but none fit the data. In 2016, researchers claimed comets 266P/Christensen and 267P/Gibbs were in the right area, except they weren't. Neither comet was anywhere near the WOW signal's coordinates when it was detected. So what's left? Either it was a 1 in a billion fluke, a perfect alignment of cosmic noise, or the closest we've ever come to catching an alien hello. The signal's brevity makes it maddeningly hard to study. Without repetition, we can't triangulate its source or analyze its structure, yet SETI hasn't given up. Breakthrough Listen, the most ambitious search for extraterrestrial signals yet, scans the WOW region regularly, hunting for a repeat that never comes. Meanwhile, alternative theories keep bubbling up. Could it have been a naturally occurring maser, a kind of cosmic laser powered by interstellar gas? Or something stranger, like a rogue pulsar with unusual emission properties? The most haunting possibility: the WOW signal was deliberate but not meant for us. Imagine a distant civilization sweeping a beacon across the galaxy, pausing just long enough for one lucky telescope to catch a fleeting whisper before moving on. If that's true, the message wasn't lost, it was simply never ours to keep, and somewhere out there, the same signal might still be traveling, waiting for another pair of ears to hear it and write WOW all over again. When NASA Pioneer 10 and 11 spacecraft ventured beyond the asteroid belt in the 1980s, something unexpected happened. They started slowing down. Not from friction or some cosmic drag, but as if an invisible hand was gently tugging them backward toward the sun. This tiny but persistent deceleration, just a fraction of a nanometer per second squared, became known as the Pioneer anomaly, and for decades it haunted physicists as a potential crack in our understanding of gravity. At first, the anomaly seemed to defy explanation. Was it some unknown gravitational effect from dark matter, a flaw in Einstein's theory of relativity, or evidence of hidden dimensions warping space in ways we couldn't see? The mystery deepened when other probes like Galileo and Ulysses showed similar deviations, though fainter. Then, in 2012, a team of researchers cracked part of the puzzle: heat. The Pioneer's radioactive power sources were emitting thermal radiation unevenly, creating a minuscule but measurable push, like the recoil from a flashlight beam. Case closed, not quite, because while thermal radiation explained most of the slowdown, some flyby anomalies refused to fit the mold. When spacecraft like Rosetta and Juno swung past Earth for gravity assists, their speeds didn't match predictions. These deviations were fleeting but undeniable, as if gravity itself had momentary hiccups. Some theorists wondered if Earth's rotation might be warping spacetime more than expected, an effect called frame dragging. Others floated the idea of modified gravity, where the laws we know break down at extremely weak forces. The wildest possibility: these anomalies might be glimpses of something deeper, a shadow force or quantum gravity effect that only appears when objects move in just the right way. Imagine the universe as a vast ocean with our current laws of physics describing the surface waves. But below, in the depths, there could be unseen currents tugging at matter in ways we're only starting to sense. The Pioneers and flyby probes might have briefly dipped into that hidden layer, revealing ripples in the fabric of reality we're still learning to measure. So while heat radiation solved part of the mystery, the rest lingers like an unfinished equation. Future missions, like those with even more precise navigational tools, could finally settle whether these anomalies are measurement errors or something far more profound. Until then, they remind us that even in the silence of deep space, the universe still has a few secrets left to whisper. In October 2017, astronomers spotted something streaking through our solar system that defied all expectations: a strange, tumbling object moving so fast it couldn't possibly be from around here. Named Oumuamua Hawaiian for Scout, it was the first known visitor from interstellar space, and it left scientists scratching their heads for years. At first glance, it seemed like a simple asteroid or comet, but the closer they looked, the weirder it got. For one thing, its shape was all wrong, 10 times longer than it was wide, tumbling end over end like a cosmic cigar. Then came the real shock: its speed wasn't just coasting on gravity. Something was giving it an extra push. The mystery deepened when researchers analyzed its trajectory. After slingshotting around the sun, Oumuamua sped up unexpectedly, as if propelled by an unseen force. Comets do this sometimes, venting gas and dust as they heat up, but Oumuamua showed no visible tail, no icy vapor, nothing. Some scientists proposed it might be releasing hydrogen gas trapped beneath its surface, a theory that could explain the acceleration without a visible coma. Others pushed back, arguing that pure hydrogen outgassing would require conditions so extreme. It was like suggesting the object was made of interstellar frost that somehow survived a journey through deep space. Then there's the light curve data, the way its brightness flickered as it spun. Those fluctuations suggested an object with wild, uneven geometry, maybe even a flattened disk tumbling chaotically. The variations were so stark they fueled wilder theories. Could Oumuamua be an alien solar sail, a thin, reflective sheet propelled by starlight? The idea wasn't entirely fringe. Projects like Breakthrough Starshot are working on similar technology right now. But with no radio signals or other signs of artificial origin, most astronomers dismissed the notion. Still, the sheer strangeness of Oumuamua forced a humbling admission. We'd never seen anything like it before, and we might not fully understand it even now. The most frustrating part, we barely had time to look. By the time telescopes swung into action, Oumuamua was already racing out of sight, leaving behind a trail of unanswered questions. Was it a fragment from a shattered planet, a bizarre interstellar iceberg, or something even stranger, a natural object so unlike anything in our solar system that it rewrites the rules? Now, the real question isn't just what Oumuamua was, it's when the next one will come. With observatories like the Vera Rubin coming online, we're about to get a flood of data on these interstellar nomads. Some estimates suggest there could be thousands passing through at any given moment, each a cryptic postcard from another star. The next time one shows up, we'll be ready. And maybe, just maybe, it'll bring answers, or better yet, a whole new set of mysteries. We measure the universe's expansion in two ways, and they stubbornly refuse to agree. On one side, we have the Hubble constant, calculated by observing nearby galaxies, exploding stars, and the flickers of pulsing stars called cepheids. These local measurements tell us space is stretching at about 73 kilometers per second per megaparsec. But then we look at the cosmic microwave background, the afterglow of the Big Bang, and the math suggests a slower rate, 67. That 6-kilometer gap might sound trivial, but after decades of ever sharper measurements, the discrepancy won't disappear. It's grown into a full-blown crisis called the Hubble tension, and it threatens to upend our most fundamental ideas about the cosmos. One explanation could be lurking in dark energy's shadow. Maybe it isn't constant as we've assumed, but evolves over time, stronger in the modern universe than in its infancy. Some tweaks propose it once interacted with dark matter, draining energy early on before surging back to dominance. Others imagine an exotic, early dark energy that briefly flared during the universe's first 300,000 years, tweaking the CMB's snapshot to make expansion seem slower than it really was. These theories aren't just fine-tuning, they're radical overhauls, suggesting dark energy's behavior might be stranger and more dynamic than Einstein ever dreamed. Then there's the measurement camp, convinced the tension is just a cosmic mirage. Could cepheids be poorer mile markers than we thought, their flickers subtly skewed by dust or metallicity? Or perhaps the CMB itself hides systematic errors, its pristine glow smudged by foreground interference. But each time researchers check, the numbers hold firm. The latest James Webb Space Telescope observations only deepen the mystery, confirming Hubble's local measurements with staggering precision, the most thrilling possibility. We're seeing cracks in the standard model of cosmology itself. Maybe gravity works differently on vast scales, or the universe isn't as isotropic as we thought. Some theorists whisper of a cosmic doppelganger, a mirror sector of particles subtly warping expansion. Whatever the answer, the Hubble tension isn't just a disagreement over numbers. It's a battle for the soul of cosmology, where every attempted fix either fails or demands rewriting physics. So is it a glitch or the first tremor of a revolution? The clock is ticking, and the universe isn't giving up its secrets easily. Deep in the cosmic microwave background map lies a chilling anomaly, a sprawling cold spot so vast it defies conventional explanation. Stretching nearly 2 billion light-years across, this eerie region is significantly cooler than its surroundings, as if a cosmic freezer door swung open in the primordial universe. When the Planck satellite mapped the CMB's subtle temperature variations, this spot stood out like a frosty thumbprint, sparking debates that still rage today. At first, astronomers thought it might be a supervoid, an enormous bubble of sparse galaxies where matter is unusually thin, causing light to lose energy as it traverses the emptiness. But detailed surveys found the void wasn't nearly large enough to explain the temperature drop. The numbers just didn't add up. Then came the mind-bending alternative. What if this cold spot isn't a flaw in the data but a bruise? A relic from a collision with another universe? Inflation theory suggests our cosmos might be one bubble in an endless multiverse foam, where neighboring universes occasionally bump into each other. If such a collision happened early enough, it could have drained energy from that patch of space, leaving behind a cosmic cold sore. Picture two soap bubbles grazing each other. The point of contact would stretch and deform, creating a subtle dimple. In this case, the dimple might be etched into the very fabric of reality, preserved in the CMB like a fossil. Critics argue it's a statistical fluke after all. With trillions of pixels in the CMB map, some region had to be the coldest. But the odds of a spot this extreme appearing by chance are less than 2%. Supporters counter with simulations showing how a multiverse collision could precisely reproduce the cold spot size and temperature profile. The truth might lie in future experiments like CMB S4's ultra-high-resolution scans, which could hunt for secondary signatures, perhaps a telltale polarization pattern or gravitational lensing distortion unique to a cosmic crash. For now, the cold spot remains one of the most tantalizing enigmas in cosmology. It's either a cosmic coincidence, a gap in our understanding of voids, or something far more profound. A window into the multiverse, a scar from a reality beyond our own. And if it is evidence of another universe, then the implications are staggering. We might be living in a cosmos that's not just vast but crowded, one of countless bubbles brushing against each other in the dark, leaving behind traces we're only beginning to decode. Galaxies shouldn't defy gravity's rules, yet one cosmic rebel does. NGC 1052 DF2, a ghostly galaxy floating 65 million light-years away, weighs in shockingly light. When astronomers measured its star's motion, expecting the telltale grip of dark matter's invisible hand, they found near silence. The stars drifted lazily like leaves on a pond, as if the galaxy's gravity came solely from the matter they could see. The discovery sent shockwaves through cosmology. How could an entire galaxy lack the dark matter scaffolding that supposedly holds the universe together? Initial measurements suggested DF2 was nearly 98% dark matter free, an impossibility under standard models. Rival teams scrambled to check the numbers. Some argued the distance to DF2 was miscalculated, throwing off mass estimates. Others proposed its stars might be concentrated in ways that mimic low gravity. But follow-up studies with Hubble and the Keck Observatory only deepened the mystery. DF2 wasn't alone. Its neighbor, DF4, showed the same eerie lack of dark matter. If these galaxies formed without the universe's most abundant ingredient, our theories might need rewriting. Enter modified Newtonian dynamics, a controversial alternative to dark matter. Mund suggests gravity behaves differently at cosmic scales, eliminating the need for invisible particles. In DF2's case, Mund predicts the observed stellar motions without dark matter. Supporters hailed the galaxy as proof dark matter is a mirage. Yet critics fired back. If Mund were correct, all galaxies should fit its modified equations, not just outliers. The debate rages in academic journals, with each side scrutinizing DF2 like a cosmic Rorschach test. The wildest possibility, DF2 might be a stripped galaxy, its dark matter ripped away in a violent encounter. Simulations show galaxy collisions can tear dark matter halos from their stars, leaving behind ghostly survivors. Yet DF2 shows no signs of such trauma. Its structure remains eerily pristine. Whether cosmic fluke or revolution in the making, DF2 forces us to confront an uncomfortable truth. The universe might be more creative than our models allow, crafting exceptions to rules we thought unbreakable. And if just one galaxy can upend decades of dogma, what other surprises are hiding in the dark? One moment, the radio telescope's feed is silent. The next, a pulse of energy brighter than a billion suns floods the receiver, then vanishes, all in less time than it takes to blink. These are fast radio bursts, or FRB cosmic flashbulbs popping across the universe. Each one packing more energy than our sun emits in days into a single millisecond. First detected in 2007, these bursts arrive without warning, often from billions of light-years away. Their origins so enigmatic that even the most cautious astronomers admit this shouldn't be possible. At first, astronomers wondered if these were one-time cataclysms colliding neutron stars, evaporating black holes, or the death throes of exotic stars. Then, in 2016, something changed. The Arecibo Observatory caught an FRB that repeated, flashing sporadically from the same patch of sky. Suddenly, the field split. Were these isolated explosions or something more deliberate? The discovery of FRB 121102, a prolific repeater in a dwarf galaxy 3 billion light-years away, only deepened the puzzle. Its bursts weren't just random, they followed rough patterns like a heartbeat with occasional skips. Theories erupted. Could these be magnetars, highly magnetized neutron stars snapping under cosmic strain, their crusts fracturing in stellar quakes that unleash radio shockwaves? Then came the CHIME telescope in Canada, a game-changer. Designed to scan vast swaths of sky, CHIME began catching FRBs by the dozens, including bursts with bizarre, downward drifting frequencies like a cosmic slide whistle. Some bursts even arrived with polarization twists, hinting at extreme magnetic environments. Yet the real stunner, a few FRBs seemed to originate inside our own galaxy, tied to a known magnetar, SGR 1935 plus 2154. For the first time, astronomers had a smoking gun. At least some FRBs came from these spinning, magnetic monsters, but not all fit the mold. Some bursts are too energetic, too clean, too structured to easily explain. Which raises the elephant in the room. Could a handful of these signals be something else entirely? When FRB 121102's bursts were analyzed for periodicity, a few researchers noted eerie resemblances to idealized beacon intervals, the kind a civilization might use for propulsion or communication. It's a fringe idea, but not impossible. After all, humanity's own radar transmissions could, in principle, be detected across interstellar space. The most tantalizing clue lies in what FRBs leave behind. Some bursts arrive with a telltale smear, a delay caused by traversing vast clouds of ionized gas. This dispersion measure acts like a cosmic odometer, letting astronomers calculate how much material the burst plowed through before reaching us. Multiply that by thousands of FRBs, and suddenly you've got a 3D map of the universe's hidden matter, traced in radio whispers. So are FRBs nature's Morse code, magnetar screams, or something else entirely? The truth might be all three. Like lightning on a stormy night, they could be a phenomenon with multiple triggers, some natural, some still waiting for their explanation. With every new detection, we're peeling back layers of a cosmic onion. one that might hide answers not just about dying stars, but about the universe's most elusive secrets. And the next burst could be the one that changes everything. Atoms are built on a simple rule. Protons and neutrons stick together, bound by the strong nuclear force, but neutrons alone. They're supposed to repel each other like magnets flipped the wrong way. Yet in 2016, physicists in Germany smashed lithium atoms into a beryllium target and caught a ghostly signal, 4 neutrons briefly dancing as a single particle. This was the tetraneutron, a cluster with no protons, no charge, just 4 neutrons clinging together in defiance of everything we know about nuclear physics. If confirmed, it would shatter textbooks overnight, because in our current understanding, this shouldn't exist. Neutrons solo are notoriously unstable, decaying into protons within minutes outside an atomic nucleus. Pairing them is hard enough, but the strong force simply doesn't have the range to bind them without protons mediating the interaction. Yet the data from the GSI lab suggested a tetraneutron surviving for a billionth of a trillionth of a second, a fleeting eternity in particle physics. Follow-up experiments in Japan and France have since reported similar anomalies, each time with that same tantalizing hint. Neutrons might have a secret handshake we don't yet understand. The implications ripple outward. If tetraneutrons can form, even briefly, they might be lurking in the ultra-dense crusts of neutron stars. These stellar corpses squeeze matter so tightly that neutrons practically overlap, creating a quantum playground where exotic particles could flicker in and out of existence. Some theories suggest tetraneutrons might be stepping stones to stranger states like quark matter, where neutrons dissolve into a soup of free-floating quarks. Picture a neutron star's crust as a pressure cooker, forcing neutrons into configurations so bizarre they'd make the periodic table unrecognizable. Now the real question: could stable tetraneutrons exist? If they do, they'd carve a whole new column on the periodic table, an element with 0 protons, just neutrons. Chemistry as we know it relies on proton count defining an element's identity. But a stable neutron-only element would rewrite the rules, opening doors to materials with properties we can't even imagine. Imagine a neutron crystal impervious to electromagnetism, its structure held together purely by the strong force. Or a neutron-based molecule, if such a thing could exist, interacting with normal matter only through gravity. For now, the tetraneutron remains a tantalizing maybe. Critics argue these signals could be statistical flukes or experimental noise, but if future labs pin it down, we won't just be adding a new particle to the list. We'll be staring at a crack in the foundation of nuclear physics, one that might lead us to the universe's most extreme, unseen realms. The Big Bang left behind cosmic fingerprints: hydrogen, helium, and a dash of lithium. The elemental building blocks cooked up in the universe's fiery first minutes. But when scientists tally the lithium-7 scattered across ancient stars, something doesn't add up. The numbers are off by a factor of 3. Where did the universe's missing lithium go? According to Big Bang nucleosynthesis models, the primordial soup should have forged far more lithium-7 than we actually detect. One theory points the finger at stars, especially red giants, which can burn lithium in their cores like cosmic furnaces. As these stars churn their outer layers, they might destroy lithium faster than they produce it, scattering the evidence across space. Yet even this stellar destruction can't fully account for the shortage. The deficit is too large, too consistent across different galactic environments. Then there's the wild card, primordial black holes. These hypothetical relics from the universe's infancy could have formed with masses as light as an asteroid. If they swarmed the early cosmos, they might have devoured lithium-rich gas before stars could even ignite. Picture trillions of tiny gravitational traps, each one gulping down lithium like cosmic Pac-Men, erasing it from the observable record. Some simulations suggest these mini black holes could have evaporated by now, thanks to Hawking radiation, leaving behind only the lithium gap as their calling card. But the plot thickens. Recent observations of the interstellar medium reveal pockets where lithium-7 is mysteriously overabundant, as if it was hoarded in some regions while others were picked clean. Could galactic magnetic fields have segregated lithium, sweeping it into cosmic dust bunnies? Or did an unknown nuclear process hijack lithium, transforming it into heavier elements? The most tantalizing clue lies in neutron star mergers. When these ultra-dense corpses collide, they forge heavy elements like gold and platinum, but theorists speculate they might also shred lithium in the process. If true, the missing lithium isn't lost. It's locked away in the aftermath of the universe's most violent dances, hidden in the wreckage of dead stars. So is the lithium problem a flaw in our Big Bang math, or evidence of something stranger lurking in the cosmic shadows? Every ancient star we study is a time capsule, holding clues to a mystery written 13.8 billion years ago. And until we crack it, the universe's elemental ledger remains stubbornly unbalanced. For 20 years, beneath the quiet mountains of central Italy, a team of scientists has claimed to hear the faint whisper of dark matter, and no one can agree if it's real or an elaborate cosmic illusion. The Dama/Libra experiment, nestled deep underground in the Gran Sasso National Laboratory, has reported a signal like clockwork. Every June, their detectors light up with a tiny surge of energy, fading again by December. This seasonal dance matches exactly what you'd expect if dark matter particles were flowing through Earth as we orbit the Sun, riding the galactic current like a river of invisible ghosts. The stakes couldn't be higher. If Dama right, they've not only caught dark matter but decoded its rhythm, a discovery worthy of a Nobel Prize. But here's the wrench in the gears. Dozens of other experiments, from LUX to Xenon to Panda X, have gone looking for the same signal and found nothing. Zip nada, the scientific community is torn. Some insist Dama seeing something real, maybe not dark matter, but something, while others suspect it's an artifact, a quirk of the detector, or even local geology. One leading alternative, cosmic muons. These high-energy particles, born from collisions in Earth's atmosphere, rain down constantly, and their flux also varies with the seasons. Could Dama's signal be muons mimicking dark matter's signature? The team maintains their shielding rules this out, but skeptics aren't convinced. Then there's the possibility of mundane contaminants, trace radon gas in the lab, or even temperature fluctuations, though Dama engineers have spent decades ruling those out. The plot thickens with theories beyond the standard dark matter playbook. Could Dama have stumbled onto a type of particle no other experiment is designed to catch? Some models suggest dark photons, or weakly interacting massive particles, WIMP with unusual properties, might slip past other detectors while triggering Dama sodium iodide crystals. It's like searching for a burglar who only trips one specific alarm wire, maddeningly specific, but not impossible. Now, a new generation of experiments is rising to the challenge. Cosine 100, using identical materials to Dama, aims to replicate the signal under controlled conditions. Meanwhile, projects like Sabre are hunting for the same modulation in the southern hemisphere, where seasonal effects should flip a telltale cross-check. If these efforts confirm Dama finding, it'll be the breakthrough of the century. If not, the mystery will deepen, leaving us to wonder, is Italy sitting on a Nobel Prize, or the most stubborn red herring in modern physics? High above Earth, hidden in the glare of the sun, something metallic has been circling our planet for decades, or so the story goes. The Black Knight satellite is one of space's most enduring legends, an ancient alien probe, silently watching humanity since before the dawn of civilization, its origins lost to time. Conspiracy theories claim it's been transmitting signals for thousands of years, spotted by Nikola Tesla in 1899 and tracked by NORAD in the 1960s. The truth, however, is far stranger and reveals how easily mythology can eclipse real science. most black night sightings trace back to mundane objects. In 1960, the US launched Discoverer 5, a spy satellite cloaked in secrecy, which left behind a reflective thermal blanket that tumbled through orbit for years. The debris caught sunlight at odd angles, creating flashes mistaken for something far more sinister. Decades later, astronaut photos of loose insulation from the ISS fueled fresh rumors, their jagged edges resembling some ancient armored craft. But the real twist, there are unexplained objects orbiting Earth, just not alien ones. Take 2020 SO, a mysterious visitor detected by telescopes in September 2020. Initially pegged as an asteroid, its trajectory and low speed hinted at something artificial. Turned out it was a Centaur rocket booster from NASA, a failed 1966 Surveyor 2 mission, wandering the solar system for 54 years before gravity finally called it home. This is how UFO myths distort real discovery. The Black Knight legend thrives on a mix of misidentified debris, Cold War secrecy, and the human brain's knack for seeing patterns in chaos. Yet buried in the noise is a genuine mystery. Space is littered with forgotten relics of our own making, dead satellites, discarded boosters, even a floating glove lost during a Gemini spacewalk. These objects outnumber the stars in some orbital lanes, their origins often unknown until painstaking detective work unravels their past. So why does the Black Knight persist? Because it taps into something deeper than facts, a longing for cosmic company, a whisper that we're not the first to reach for the stars. Every unidentified blip on a radar screen becomes a canvas for our imagination, a Rorschach test against the infinite. The irony, humanity has built ancient satellites. Vanguard 1, launched in 1958, still orbits today, the oldest human-made object in space. It's not an alien observer, just a silent witness to how quickly myth can outshine metal. The next time you hear about the Black Knight, remember, the universe doesn't need aliens to be strange. Our own debris tells tales wild enough without inventing extraterrestrials. And somewhere up there, among the real mysteries, a thermal blanket still tumbles through the void, waiting for the next curious mind to mistake it for a messenger from the stars. What if everything around you, the stars, the air you breathe, even the device you're using right now, is nothing more than lines of code in an unfathomably advanced simulation? This isn't the plot of a sci-fi movie. It's the simulation hypothesis, a serious argument championed by philosopher Nick Bostrom that suggests we might all be digital minds in someone else's cosmic computer game. His reasoning hinges on three unsettling possibilities. Either civilizations never reach the tech level to create simulations, they choose not to run them, or we're almost certainly living in one right now. Given the explosive growth of computing power and humanity's own obsession with virtual worlds from video games to AI training environments, the third option starts to feel uncomfortably plausible. Think of it like this: if future civilizations could run hyper-realistic ancestor simulations, recreating their past with flawless detail, the number of simulated minds would dwarf the population of the real physical universe. Statistically, you're more likely to be one of those simulated beings than an original. And if that's true, reality might be hiding glitches, tiny imperfections in the rendering. Physicists have even looked for these cosmic pixels by probing the fabric of space for signs of energy quantization, like a digital image breaking down when you zoom in too far. Some studies of ultra-high-energy cosmic rays suggest bizarre, pixel-like limits to how energy distributes in the vacuum of space, as if the universe has a built-in resolution cap. Then there's the Fermi paradox's eerie twist. If simulations are common, advanced civilizations might quarantine their creations to prevent rogue AI or ethical dilemmas. That could explain why we've never detected aliens. They're not out there because we're the ones in a box. Others propose the Mandela effect, where collective false memories like Nelson Mandela dying in prison are literal software patches, updates where the programmers tweak details and some users don't get the memo. But here's the real cliffhanger: if we're in a sim, who's running it? A post-human society studying history like a living museum? A bored teenager in a civilization a trillion years ahead of us? Or something even stranger, an AI that spawned its own simulations, creating infinite nested realities where every sentient program thinks it's the original? The simulation argument doesn't just question reality, it forces us to ask what it means to be real at all. And until we find that telltale glitch in the matrix, the universe's biggest secret might be hiding in plain sight, written in the code we haven't learned to read. From the ghostly whispers of quantum foam to the cosmic scars left by ancient strings, these 30 hidden forces paint a picture of a universe far stranger than we ever imagined. They're the invisible architects behind everything we see, and yet everything we can see is just a sliver of reality. The stars, the planets, even your own reflection in the mirror, they're only 5% of the cosmic ledger. The rest, a vast, uncharted frontier of dark matter, dark energy, and phenomena so bizarre they still defy our best theories. Think of it like standing in a hall of mirrors where every reflection reveals another layer of deception. We thought we understood gravity until galaxies spun too fast and forced us to invent dark matter. We mapped the cosmos only to find it expanding faster and faster, driven by an enigmatic force we can't even detect. Even the vacuum of space itself isn't empty, it's a boiling sea of virtual particles, a quantum storm that might hold the key to the universe's greatest mysteries. The beauty is in the unanswered questions. Could dark matter be an entire shadow universe overlapping our own? Is the Higgs field teetering on the edge of catastrophe, one quantum fluctuation away from rewriting physics? Every discovery peels back another layer, and with each one we realize how much we don't know. That's the thrill of science, not having all the answers, but knowing there's always another puzzle to solve. So here's the challenge: which of these forces fascinates you? Is it the phantom tug of the Great Attractor dragging galaxies toward an unseen behemoth? The chilling possibility of vacuum decay lurking in the space between atoms? Or the eerie whispers of fast radio bursts crackling across the cosmos like coded messages? The debate is just beginning. Drop your thoughts below and let's unravel these mysteries together. And if you're hungry for more cosmic secrets, hit subscribe. The universe isn't done surprising us